Hello, good morning, all of you. Welcome you all for today's session uh, on gate structural engineering gate classes funded by AICTE Prerana, conducted through CMR Institute of Technology, Bengaluru. So, in today's session, we'll discuss about structural analysis, which comes under section 2 in the gate syllabus civil engineering, structural engineering. So engineering mechanics, we have already discussed. Solid mechanics, we have already discussed in our previous session. And in our today's session, we'll discuss about structural analysis. So syllabus is like this: statically determinate and indeterminate structures. Those analysis by force and energy methods. Method of superposition, which is already covered in strength of materials. Analysis of trusses, arches, beams, cables, and frames. Okay, and then displacement methods, the analysis of structures by slope deflection method, moment distribution methods, influence lines, stiffness and flexibility methods of structural analysis. So this is the syllabus, which includes both analysis of statically determinate and indeterminate structures by different methods of analysis. So let us start with the scratch statically determinate and indeterminate structure. What does it mean, and what is the difference among these two? So structures are said as statically determinate if these structures can be analyzed by using conditions of equilibrium. All of you know the conditions of equilibrium, that is a summation of V equal to 0, summation of H equal to 0, and summation of M equal to 0. In place of summation of V and summation of H, other notations like a summation of Fx and a summation of Fy, like that you can use. So such structures are termed as statically determinate structure. And those structures which cannot be analyzed by using only these three conditions of equilibrium, such structures are said to be statically indeterminate structures. However, these structures can be analyzed by some other methods and also by using compatibility conditions. And the difference between these two, in case of a statically determinate structure, stresses will not be caused due to change in the temperature. Where in case of indeterminate structures, stresses are caused due to change in temperature. And in case of a statically determinate structure, no stresses are caused due to lack of fit, but where in case of statically indeterminate structure, stresses are developed due to lack of fit. These are all the differences. And some examples for statically determinate, it is a simply supported beam, cantilever beam, ranged arches. Okay, these are all some examples. So these structures can be analyzed by using the three conditions of equilibrium which I showed. That is summation of V equal to 0, summation of H equal to 0, and summation of M equal to 0. And some examples for a statically indeterminate structure, that is fixed beam, propped cantilever beam, and two hinged arches. So these structures cannot be analyzed by using only those three conditions of equilibrium. So this requires some more compatibility conditions and some other methods we can use for the analysis. Now you come for static and kinematic indeterminacy. Static indeterminacy is nothing but a degree of redundancy of a structure. The meaning of this, or the definition: the number of equations required over and above the equations of static equilibrium. Okay, over and above the equations of static equilibrium. We know those are three conditions of equilibrium, static equilibrium conditions. So over and above these three conditions of equilibrium, how many number of equations are required for the analysis of structure? So that number is nothing but the degree of redundancy, or nothing but static indeterminacy. Okay, So that is what the meaning of this. And then degree of kinematic indeterminacy or degree of freedom. That means the number of equilibrium conditions needed to find the displacement component of all joints of the structure. So that is known as a degree of freedom. Basically, how many number of equilibrium conditions we need to analyze a structure. That is what degree of freedom. And degree of freedom for different structures. Some examples, like if you consider a free end, okay, the free end is free to rotate, free to translate in two directions. So this free end is having 3 degree of freedom. For the analysis of this three free end, it is required 3 equations of equilibrium. So that is what the degree of freedom is, which is nothing but degree of kinematic indeterminacy. When you come for a simple support or roller support, it will offer the reaction in only one direction, that is normal to the uh, surface which is resting on that. So this roller support or simple support, it is free to rotate and it is free to translate in one direction. So the degree of freedom for this, it is 2, and in only one direction it is offering the reaction or resistance. So it is not free to translate in one direction. So totally degree of freedom is 2 for simple support or roller support. And if you consider hinged support, so translation is not possible, only rotation is possible. So it is free to rotate. So degree of freedom of a hinged support, it is 1. And when it comes to fixed end, it is firmly held. It is not free to rotate and it is not free to translate. It is held in position firmly. So the degree of freedom for fixed end, it is 0. Okay. So the degree of freedom means the number of displacements allowed at the joints of a structure. Okay, how many displacement components or displacements are happening at a joint? So that is nothing but degree of freedom. Now you come for mathematical formulation and the calculation. Formula for degree of redundancy or degree of static indeterminacy. It is the degree of static indeterminacy equal to actual number of reactions, which are nothing but unknowns. How many number of unknowns are there? The number of unknowns minus available number of equations minus number of internal hinges if exists. Okay, so actual number of reactions or actual number of unknowns minus available number of equations minus number of internal hinges. So that is degree of redundancy. And this same formula for different type of structures. When it comes to 2D trusses, it is the degree of static indeterminacy, that is En suffix s. So this is degree of static indeterminacy equal to m plus r minus 2j, where m is the number of members, r is the number of reactions, and j is the number of joints, including supports. Okay, m plus r minus 2j. So that is for 2D trusses. When it comes to 3D trusses, the degree of a static indeterminacy is equal to m plus r minus 3j. In place of 2, here it is 3 displacement components. This is a plane truss, this is space truss. Okay. And when it comes to 2D beams and frames, the degree of static indeterminacy is equal to 3m plus r minus 3j. If you multiply 3 to m, 3 to j, you will get 3m plus r minus 3j minus t. So here t is nothing but the number of releases, like number of internal hinges. Okay, that should be deducted. So that is degree of static indeterminacy. And for 3D beams and frames, it is 6m plus r minus 6j minus t. Okay, terms are already explained. So these formulas you need to remember. If you remember these formulas, it is easy to calculate the degree of static indeterminacy. Okay. So some examples. Here we have taken one plain truss. So it is 2D. So 2D truss means, which is the formula? 2D truss m plus r minus 2j. So here we have to count how many number of members are there, how many number of reactions, and how many number of joints for calculation of degree of static indeterminacy. So the number of joints A, B, C, D, E, F, G, H. Okay, totally 1, 2, 3, 4, 5, 6, 7, 8. So 8 number of joints are there. So that is shown over here, j equal to 8. And when it comes to number of members, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Number of members over here, it is 15. And number of reactions. So A is hinged support. So number of reactions offered at hinged support, it is 2. And B is roller support, and C is also roller support. So each support 1 reaction. So at B 1, at C 1. So 2 plus 1 plus 1. So totally 4 number of reactions. So we are done with this M, R, J. And however, internal hinges does not exist in case of trusses. So degree of static intensity formula we have written, and you substitute M is 15 plus R is 4 minus 2J. J is 8. So 15 plus 4, it is 19. 8 to it is 16. So 19 minus 16. The degree of static indeterminacy of this truss is 3. 19 minus 16. Okay, very simple to calculate if you remember formula. And some more examples. We have taken one 2D beam over here, a propped cantilever beam, roller support over here, fixed support over here. So when it comes to fixed support, the number of reactions, it is 3. When it comes to roller support, the number of reactions is 1. So 3 plus 1, it is 4. So 4 number of reactions. So that is why it is written R equal to 4. And the number of members, it is only one beam from here to here. So number of members M is 1. And number of joints is, here it is 1, here it is 1. Totally 2 number of joints. So you have the data M, R, J. And the formula for calculating degree of static indeterminacy here is 3M plus R minus 3J. So 3M means M is 1. So 3 into 1, it is 3. 3M plus R is 4. So 3 plus 4, it is 7 minus 3J. So 3 into J is to 6. So 3M plus R value, it is 7. 3J, it is 6. 7 minus 6 is 1. So this D is nothing but degree of static indeterminacy. The degree of static indeterminacy, it is 1. To apply the same for other structure, the same formula. This is also beam. So this is an arch. This is a frame. Okay. 3M plus R minus 3J formula you can apply. Here, when it comes to this arch section, one side it is fixed support and another side it is hinge. So fixed support, 3 number of reactions, and hinged support or pin jointed, it is 2 number of reactions. 3 plus 2, it is 5, and number of member, it is 1. So 3M plus R. 3M means 3 into 1, that is 3, plus R is 5. So 3 plus 5, it is 8, minus 3J. So 3 into 2, it is 6. So 8 minus 6 equal to 2. So degree of static indeterminacy is 2. Okay. So very simple, and multiple floors and one frame you consider here. So totally 4 columns are there and beams are running through 1, 2, 3, 4. 4 supports, all are fixed support. So that means each support offer 3 reactions. So 3 into 4 number of fixed support, it is 12 number of reactions. And then number of members, it is 1, 2, 3. So 3 number of members, 3 segments, totally 9. And then 1, 2, 3. So 3 number of members, totally 4, it is 12. So 12 plus 9, it is 21. Number of members, it is 21. So R is 12. And number of joints, if you count, 1, 2, 3, 4. So 4 number of joints in each column, totally 4 columns. So 4 fours are 16. So 16 number of joints. Okay. So as this is a plane frame, again the formula, it is 3m plus r minus 3j. So if you calculate, you are going to get the degree of static indeterminacy of this frame as 27. So 27 is the degree of static indeterminacy. And if there exist any internal hinges, okay, you need to deduct those many number of internal hinges while calculating degree of static indeterminacy. You can read this question. Calculate the degree of static indeterminacy for the beam shown below. And if there exist any internal hinges in the plane frames or beams, okay, expression will be 3m plus r minus 3j minus number of internal hinges. So see this beam. So hinged support, roller support, and roller support. And there is an internal hinge between these two roller support. So when hinge exists like this, okay, you should consider this hinge also as a joint. So totally how many number of joints? 1, 2, 3, 4. Okay. So 4 number of joints are there. And then number of members, it is 1, 2, 3. So 3 number of members. So 3 members, 4 joints. And the number of reactions, this is hinged support, 2, roller support, 1, roller support, 1. 2 plus 1, totally 4 number of reactions. So 3m plus r minus 3j, that regular formula you know, minus n. Okay. So 3 into 3 plus 4 minus 3 into 4 minus 1 is the internal hinge. So there is a 9, 9 plus 4, it is 13, 13 minus 12, it is 1, 1 minus 1, it is 0. The degree of static indeterminacy, it is 0 for this beam. So like that, some more examples you can have it up. And you can solve on your own. So you will get a degree of static indeterminacy as 0 over here, and then minus 1 over here. This is roller support, and this is fixed support. Yeah. Next one, to come for a degree of freedom, which is nothing but a degree of a kinematic indeterminacy. And you need to remember these two formulas for just a minute. For pin jointed frames, which are nothing but trusses, degree of kinematic indeterminacy, it is 2j minus r. J is again a number of joints, and r is number of actual unknowns or reactions. And for beams, it is 3j minus r. Okay, degree of kinematic indeterminacy, it is 3j minus r. And if there exist any internal hinges, you will be adding those many number of internal hinges, that is plus number of internal hinges. So in previous case, degree of static indeterminacy used to deduct minus number of internal hinges. Where in case of kinematic indeterminacy, you will be adding the number of internal hinges, 3j minus r plus number of internal hinges. Example problems you take, there is a fixed beam, but in between there is an internal hinge. So number of reactions, 3 over here, 3 over here. So totally 6 number of reactions are there. Okay, number of joints, 1, 2, 3. So 3j minus r plus number of internal hinges, 3j. 3 into j is 3. 9 minus R is 3 over here, 3 over here, totally 6 plus number of internal hinge 1. So 9 minus 6, it is 3. 3 plus 1, it is 4. The degree of kinematic indeterminacy for this structure, it is 4, or the degree of freedom. So in the same manner, if you consider a portal frame with one internal hinge at one corner, there is fixed support at one end, hinged support at another end. So three number of reactions at fixed support, two number of reactions at hinged support. So totally 3 plus 2, it is 5 number of reactions. And then number of joints, it is 1, 2, 3, 4. 4 number of joints are there. 3j, 3 into 4 minus 5 plus 1 is internal hinge. So the degree of static indeterminacy, kinematic indeterminacy, it is 8. So apply the same procedure for this beam also. You will be getting 7 as degree of freedom or degree of kinematic indeterminacy. And when it comes to plane trusses, the formula is 2j minus r, and you can have a look on this beam. The number of joints, it is 1, 2, 3, 4, 5, 6. 6 number of joints are there, and the number of reactions over here, it is a hinged support 2. Over here, it is roller support 1. So 3 number of reactions, 2j minus r, 2 into 6 minus 3. So the answer is 9. The degree of kinematic indeterminacy of this truss is 9. Okay. So you can expect a few questions, very simple 1 mark questions like this, determination of degree of static and kinematic indeterminacy. And then analysis part, you come for the determination of internal forces in each member when it comes to trusses. Okay. So we have two methods, method of joints and method of sections, the analysis of these trusses. So in case of method of joints, we apply conditions of equilibrium at each joint and we determine the unknown actual forces of each member. Okay, that is what method of joint is. In case of a method of section, we are not going to find the actual force in each member. We will take a section, okay, in such a manner that like at least 3 members or 2 members are going to cut, and then we'll take a moment. So when we take a moment, we'll get the unknowns, specific unknowns, which we want to determine. So that is method of section. For example, for method of section, you can see over here. So section 2 we have taken in this manner. We are cutting over here. So member DF, member DC, and member EF, okay, will be the unknown forces. And if you take a moment at any one support or any point, we'll get the unknown axial forces. And you can see over here also. So we have taken section 1 in such a manner that this, and this 3 members are going to cut. And if we take a moment, we are going to get the unknown forces. That is method of section. And before analyzing the truss by any one of the method which is specified, that is method of joint or method of section, we need to know the assumptions made in analysis of trusses. So the assumption 1, the truss is perfect and the modulus of elasticity is same throughout the length of member, and the joints are pin jointed, all the joints are pin jointed or hinged. The loads are acting through joints only, not in between. The members are straight and the self weight of the truss is neglected. Okay, so these are all the assumptions made in analysis of trusses. So one simple example problem, analysis of truss by using a method of joint, first method. So this is the truss. So A, B, C, D, E, F. And here the number of members, it is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 number of members are there. And at joint C, there is a 1000 Newton force is acting. And at joint E, it is 1000 Newton force is acting. Okay. So before analyzing whether it is a statically determinate or indeterminate can be checked. So m plus r minus 2j, you know that. So m is 9, j is 6. So m plus 2 into m plus r is minus to minus plus. So it is r is 3 minus 2j, it is 2 into 6. So this is degree of static indeterminacy. Okay. You just check this. So it is 3, 9 minus 6 into 2, it is 12 plus 3. So 12 minus 12, it is 0. So it is statically determinate structure. And then analysis part if you come for. So in the analysis, first we need to determine the reactions, support reactions first. So in this truss, so at A it is roller support, at F it is hinged support. So at A only one reaction will be offered by the support vertically up. We can say that as R suffix A. At joint F, two reactions will be there. So if we take a resultant reaction at F, we can call it as RF. And this resultant acting in vertical direction, the vertical component of RF, it is RFY. That is the notation we are using. And RF X equal to 0 directly we can say because there is no horizontal force on this truss. Okay. So the vertical component of RF, that is RFY, will be using. So let us apply the conditions of equilibrium to determine the support reaction of this truss. Summation of Fx equal to 0. Okay, so the horizontal component of RF, that is RFX equal to 0. And summation of Fy equal to 0. So that means at A, RA is acting towards up. At F, the vertical component of RF, that is RFY, is acting upwards. So RA plus RFY minus towards down at C and E, 1000 equal to 0. So you'll get an equation RA plus RFY equal to 2000. And then third condition of equilibrium, that is moment at any point you can take. So summation of moment at A equal to 0 we are taking. So from here the forces 1000 towards down and perpendicular distance 3 and trying to rotate in clockwise with respect to A. So 1000 into 3 positive. And then if you take a moment of this 1000 Newton force, the perpendicular distance is 3 plus 3, 6. So 1000 into 6 trying to rotate in clockwise positive. And then vertical component of RFY, RF is RFY. So RFY, it is acting towards up and perpendicular distance is 9, trying to rotate in anti-clockwise direction. So RFY into 9. Okay, that is minus. You can have a look over here. 1000 into 3, 1000 into 6 minus RFY into 9 equal to 0. So RFY equal to 9000 divided by 9, RFY equal to 1000. So you have equation that is RA plus RFY equal to 2000. If you substitute for RFY value that is 1000, you will get value of RA as 1000. Okay, we are done with finding out the support reaction. Now we can apply conditions of equilibrium at each joint so that we can determine the axial forces. First, let us consider joint A. So at joint A, two members are there and one support reaction is there. So member AB and member AC. So initially let us consider these two members are subjected to an axial tension force. So based on sign convention, we can later get to know that whether it is tension or compression force it is subjected to. So tension force normally we show with an arrow mark away from the joint. So this is joint A, 1000 Newton force towards up it is acting, already determined force this is. And FEAC away from the joint and FEAB away from the joint. And this angle, it is 45 degree. How we can calculate this? So 3, it is vertically up and 3 over here. So tan theta equal to opposite by adjacent. So theta equal to tan inverse of 3 divided by 3. If you do so, you are going to get 45 degree. And assume that members AB and AC are under tension. Already we assumed this. And let us start to apply the conditions of equilibrium at this joint. Summation of Fy equal to 0. First condition of equilibrium we are applying. So 1000, it is acting upwards, positive. And then FEAC, it is truly acting horizontal. There is no vertical component of this. And when it comes to AB, FAB, the vertical component, of this FAB, if you resolve, it is FAB sine 45. So that is plus FAB sine 45 equal to 0. So FAB equal to 1000 divided by sine 45, we will get minus 1414.214. So this minus this sign convention is indicating that, so this member is not subjected to tension. This member is subjected to compression force. So that is why we have written it is C. And then we need to determine FAC also. The other condition of equilibrium, that is summation of Fx equal to 0. I'm applying now. So horizontally towards right, FAC plus, and then FAB is also like horizontal component of FAB, it is towards right, that is FAB cos 45. So FAC plus FAB cos 45 equal to 0. FAC equal to 1414.214 cos 45. So that you will get plus 1000 Newton. So our assumption is correct. So initially we assumed that AC member is subjected to tension force. We got the answer in with positive sign. So this is for at one joint, applying conditions of equilibrium and determining the unknowns. So we applied the condition of equilibrium at joint A, and we determined the axial force in member AB and AC. And now the same procedure we should continue for other joints. So other joint means like we have two options over here, that is B and C. So we have the freedom to opt any joint, but we should be smart enough to choose which particular joint we should go for. If you have a look on joint B, the member force in AB is already determined, and member force in BC and BD we have not determined. Okay, only two unknowns are here. AB already determined. When you see this joint C, the member force AC we have, but member force CB, CD, CE we do not know. So more number of unknowns are there at joint C. So it is good to choose or go for analyzing at joint B rather than at joint C. So same procedure you apply, draw free body diagram at joint B. So this is AB, we already got to know that this is subjected to compression. Okay. So the free body diagram at joint B, see here, arrow mark is towards the joint FAB because it is subjected to compression. And member BD and member BC, we are showing away from the joint. We are assuming that these two members are subjected to tension force, and this is 45 degree. Summation of Fx equal to 0, summation of Fy equal to 0. So summation of Fx means FBD and FAB. Only these two components will come. However, we have the value of FAB, so that we will get FBD. And then a summation of Fy, if you apply FBC and FAB, only these two components will come. If you substitute for value of FAB, you will get FBC. So like this, we have applied the same conditions of equilibrium at all the joints, and finally we get the member forces in all the members. Okay. So the analyzed results is tabulated over here. Member AB is subjected to compression force if the answer is with a negative sign convention. And then member BC, 1000, subjected tension. Okay, you can have a look. and the member CD is subjected to zero axial force. There is no force at all at this member, that is C. Okay. Sometimes the questions may be like which particular member is like the which of the following member, the actual force in the member is zero. So like that, some MCQs may be there. So in such cases, directly like you can figure out by looking the geometry and the joint where exactly the member force is acting. Okay. So this is one example for a method of joints. And when it comes to method of sections, okay, there is a truss A, B, C, D, E, F, and at joint B, C, D, 5 kilonewton force is acting in such a manner that it is perpendicular to the line BCD. And there is another force, 40 kilonewton, acting at joint B only. Vertical height 3 meter. The span is 9 meter. Okay. So in this, again, you should start with finding out the support reactions. That is a support reaction at A and a support reaction at D. We can determine. After determining that, here in question it is specified. We have to determine the member forces BC, CF, EF, and CE. Okay, by looking at this, where exactly we should take the section, we'll get to know. So BC is here, CF is here, EF is here, and CE is here. So we cannot cut all the members in a single section line. So we can take a section vertically, vertical line if you draw over here. It is going to cut the member BC, CF, and EF. So like that, we can cut and we can take the moment and we can find out the unknown forces. And later, we can take another section 2, 2. It is shown over here. 2, 2 in such a manner that member CD, member CE, and member FE are going to cut. Okay. So first, once you cut like this, section 1, 1, you will get the free body diagram like this. FBC, FCF, FEF. Okay. So all members are subject to tension, we have assumed. So later we'll confirm based on suspension. So this is the procedure which is given here for the determination of support reactions, RAY, RAX, and RD, that you know, and how to determine the member forces. Okay. See here, we can take a moment about D in this. If you take a moment about D, okay, RAY into 9 minus 5 into 6.708. So this 6.708 is this distance from B to D. Okay, half of that 3 point something will come. If you take a moment about this for determination of support reaction, you need to take a moment of this 40 kilonewton force, this 5 kilonewton each, and then this RAY. That is what it is done over here, so that RAY and RD is determined. So after that, from this cross section or free body diagram, we are taking like we are trying to determine these unknown forces FBC, FCF, and EF. Summation of Fx, summation of Fy, and summation of M about any point or joint can be used again. So here, this first line, this is, we have applied the condition of equilibrium, summation of horizontal forces equal to 0. That means FEF, it is a horizontal. Towards left means you can maintain sign convention minus FEF, and then FCF, the horizontal component of this is FCF sine 26.56 or cos 26.56. So again, that is minus sign convention. Horizontal component of FBC, it is FBC cos 26.56, that is again minus. And then when it comes to this 5 kilonewton force, it is at an angle of inclined at an angle of 63.44 degree. That you need to calculate, because this 26.56 you have already calculated. So 90 minus of that is 63.44. Horizontal component of this is 5 cos 63.44 towards left minus, and two components of 5 5, it is multiplied by 2. So minus sign convention for all the terms, you can send that minus towards RHS side, so that everything will become positive. So you got equation with three unknowns, FEF, FCF, and FBC. So in the same manner, you apply summation of Fy equal to 0 for the same free body diagram. You will get this equation with unknowns FBC and FCF. So two unknowns are here, FBC and FCF. Okay. So and then FEF, FCF, and FBC. So this particular equation is simplified and rewritten over here, and this constant value is sent to RHS side, so that minus 10 cos 63.44 it will become. And then this equation is rewritten over here in such a manner that it will come FCF, FCF, FBC, FBC in this manner. Okay. So we have three unknowns in first equation, we have two unknowns in second equation. So three unknowns, so three equation we may require, or we can go for applying third condition of equilibrium, summation of moment. And here we are applying summation of moment at C equal to 0. Let us have a look where exactly C is. Take a moment about C. So this member will pass through here, this member will pass through here, so that there is no moment. This 5 kilonewton is also passing through this joint C, so there is no moment due to 5 kilonewton force. There is only rotation with respect to C due to application of 5 kilonewton force here, and FEF, and then here support reaction. So those things you can have a look in this free body diagram. So RD 5, and then FEF above this point. So summation of MC equal to 0, that is FEF into 1.5 is the perpendicular distance. 5 into 3.354 is the distance, perpendicular distance. And this 21.159 into cos 26.56 into 3.354. So rather than this, directly you can multiply this RD into this perpendicular distance. This perpendicular distance, you can have a look over here, it is 3. So RD into 3, directly you can multiply. If you do so, you are going to get the unknown force FEF is a 31.15. So 31.15 is the and the sign convention for that, it is positive, so that our assumption is correct tension force. So substitute this value FEF in this equation, so that only two unknowns it will become in this equation, FCF and FBC. Same unknowns are there in this equation also. Solve these two simultaneous equations, so that you will get FCF and FBC. If you get negative sign convention, the solution will, so that it is subjected to compression force is shown here. Okay. Not it is not a lengthy procedure, the method of section, because where exactly or which particular axial force we require, directly we cut a section over there and we will determine the unknowns. So we have to determine one more unknown axial member force over here. So that is member CD. So for that, section 2.2 is taken. So in this member EF force we do have, and member CE force we do have. Only the thing is member CD force we do not have. If you substitute those two in summation of Fx and summation of Fy equal to 0 with this free body diagram, in two steps you are going to get the answer. Okay, you can have a look over here. FCD we have got minus 37.312 kilonewton. So this is the free body diagram for section 2. So that is all about method of joints and a method of section, how to analyze the trusses and determine the unknown axial forces. So next you come for the analysis of beams. So how to determine the deflection and rotation in beams. So one simple method we have, moment area method. We can easily define the deflections in the beams. We have two theorems in this method. So what theorem 1 says? Theorem 1 says the change in the slope between 2 points on a straight member under flexure is equal to the area of bending moment diagram divided by EI between those 2 points. Okay, if we take one member beam which is subjected to a flexural force, so then the slope is given by the area of a bending moment diagram between those 2 points divided by EI. So theorem 1 basically it is for finding out the slope, and theorem 2 it is for determining the deflection. So deflection at a point in a beam in the direction which is perpendicular to the original straight line position measures from the tangent to the elastic curve at another point is given by moment of bending moment diagram divided by EI about the same point. Okay, it is not area over here, it is moment of bending moment diagram. In case of slope, we are taking area of bending moment diagram. In case of theorem 2, that is for while finding out the deflection, we will take moment of bending moment diagram over here. So on the basis of these two theorems, the equation can be written as slope, that is theta equal to area of BMD by EI, and deflection equal to moment of uh, this bending moment diagram, that is x bar is the centroidal distance and area. Okay, moment of BMD divided by EI. So for the calculation purpose, you can have a look on area of different geometries, that is right angle triangle, half into base into height is the area, and for parabolic variation 1 by 3 into base into height is the area for this variation, and other half of the rectangle in a parabolic variation is this, that is 2 by 3 into base into height. Centroid is located at a distance of 5 by 8 times of this base width from 0 end, and then from base it is 3 by 8 times of horizontal distance. So in case of this, 1/3 of uh, this height and 2/3 of height from apex. So in case of this, 1/4 from base, 3/4 from apex, total distance, and a triangle of into base into height. So on a simple problem, let us have a look how to find the slope and deflection. You can read the question, determine the slope and deflection at the free end using moment area method. There is a cantilever beam, one side it is fixed end and other side it is subjected to a concentrated load of W, and span of beam it is L. So bending moment diagram, if you draw the bending moment at any section, if you take a section at a distance of X, bending moment due to this load is W into X. So if you want to determine or calculate moment with respect to this A, so W into L. So that is a moment value which is written over here. And it is hogging in nature. So negative is the sign convention for bending moment diagram. So this is a triangular portion. So that the centroidal distance is 2/3 of L from apex. And we know that the slope at B, the formula is area of a BMD between A, where slope is 0, and B, where slope is required. See, at A, it is fixed support, right? So fixed support means there is no rotation at all. The slope value at fixed support, it is 0. So that is a known value. And then we are trying to find the slope at B. So these two points we need to take. Between these 2 points, whatever bending moment area is there, that we should take. So between point B and point A, bending moment diagram area is half into base is L and height is W into L. So half into L into WL. So that is what the area of BMD between these 2 points divided by EI. And here we are showing negative sign convention for hogging bending moment. So theta B or maximum slope at B, it is minus WL square by 2 EI. Okay. See, sometimes this moment of inertia value may be different. In place of I, they may specify 2I. In such cases, you should substitute over here 2EI. So in such case, this value will become minus WL square divided by 4EI. Okay. So this is how to determine slope at B. And now, if you come for deflection at B, we'll take moment of bending moment diagram, right? So area into x bar divided by EI, where this area we will be taking between A and B again. So about B, we are taking moment of this area, half into L into WL is the area, and we should multiply this area by the distance. Centroid is located at a distance of two-third of L from B. You should multiply this two-third of L. So that is what it is done over here. Half into L into WL into two-third of L divided by EI with negative sign convention. So that minus WL cube divided by 3EI you are going to get if you substitute this. Okay, very simple. The same thing you can apply for different load system also. So for different loading system, the geometry of area may differ. Accordingly, you need to use formulas. Here, 2 point loads are there. So for that, we need to draw the bending moment diagram. So 10 into 2 meter is 20 kilonewton meter at B. And then when you take a moment at C, it is 10 into 3.5, that is 35. And then plus 20 into 1.5, it is 30. 30 plus 35, totally 65 is the moment at C. Okay. So this is how the bending moment diagram will come. And the question is calculate the slope and deflection at free end by using moment area method. So slope is 0 at C, and we need to determine slope at A. So area between these two. So totally we can divide this bending moment diagram into 3 segments: triangle, rectangle, and triangle. For calculation of rotation, area of all these 3 bending moment diagrams, splitted bending moment diagram divided by EI. And then for calculation of deflection, moment of individual, the splitted part of bending moment diagram with respect to A. So you can have a look on the calculation. So theta A equal to area of BMD between C and A, area of first triangular portion, half into base into height, half into 2 into 20, plus rectangular portion 1.5 into 20, and another triangular portion half into 1.5 into 45. So it is hogging bending moment, negative 18. So theta equal to minus 83.75 by EI. And when it comes to deflection, we'll have to take a moment of individual areas. This remains the same, half into 20, 2 into 20, 1.5 into 20. Same things will be there, but each areas will be multiplied with the distance of centroidal distance from A. So centroidal distance from A is two-third of 2 meter for this triangle, and for this rectangle 2 plus 1.5 by 2, and for this triangle 2 plus two-third of 1.5. You can see here two-third of 2, 2 plus 1.5 by 2, 2 plus two-third of 1.5. To substitute, you will be getting minus 210.42 divided by EI as the deflection at A. And when it comes to simply supported beams examples, there is a simply supported beam subjected to a point load W at mid. Bending moment diagram for this is like this. So W exactly at center it is acting means support reaction at A it is W by 2, support reaction at B W by 2. We take moment of this W by 2 about this point, W by 2 into L by 2, so that WL by 4 is the bending moment at this point. So linearly we need to join as there is no load in between these two. So this is the bending moment diagram. So the beam is subjected to sagging bending moment, and we know that from theorem 1 theta A equal to theta B, both are same over here because point load is acting exactly at center. Okay, if the point load is not acting at center means the value of theta A may not be equal to value of theta B. So theta A are equal to theta B equal to area of BMD, that is half into L by 2 into WL by 4 divided by EI, will get WL square by 16 EI. And we can take moment of this bending moment diagram for finding deflection, area into X bar divided by EI, half into L by 2 into WL by 4 into 2/3 of L by 2. Okay, 2/3 of L by 2, that is one particular triangle will be considered. Okay, we'll get a WL cube by 48 EI. The 2/3 of L by 2, why we are taking? See, where exactly the point where zero rotation or zero slope is coming in this beam? Exactly at the point where W is acting. If you draw a horizontal line, so over here, there is zero rotation. Okay, so always we should consider the area between zero rotation and where exactly we need to find the rotation. We need to find the rotation at A and zero rotation point is here. So this much area we'll have to take. So with respect to this 2/3 of F by. Okay. Even in this case also half into L by 2 into WL by 4 only we have taken. Only left half portion we have taken. So the deflection value it is WL cube by 48 EI. So some more examples. Over there it is a point load. Over here it is a UDL. For UDL, the parabolic variation will get, and left half portion only we are taking because this is a center exactly midpoint. The mid span is the point where the rotation is zero. So that from there to one side support we are taking. So area of BMD divided by EI and moment of this area divided by EI. We'll get WL cube by 24 EI and 5 times of WL raised to 4 by 384 EI. And an example where uh, the point load is not acting exactly at center. So theta A will be having different value and theta B will be having different value. Professor, you can have a look for finding out deflection, moment of area between B and A is taken. Yeah. So now you come for another type of structure, that is a 3-inched arch. How to analyze 3-inched arch? Basically 3-inched arch, initially I have given, it is a statically determinate structure, 3-inched arch. So this is the geometry, the different parts, the span, it is between distance between A to B, that is the span, and the vertical height at midspan, that is the rise, and the point, peak point, that is crown. It is named as C. And if you draw a free body diagram at supports, this is a hinged support at A, hinged support at B, and there is another hinge at crown C. So totally 3 hinges are there in this arch. And HA, VA, VB, HB are the support reaction at hinges A and B. Okay. And moment at A, moment at C, and moment at B equal to 0 because all 3 These points are hinges. So moment value will be 0 over here. And equation of a parabola for the geometry, you can remember this, y equal to 4 times of h divided by L square into x into L minus x, where h is the rise, L is the span, x is the section, where exactly we are trying to determine the ordinate height. We are trying to find the ordinate height y over here at a distance of x means if you substitute the value of x over here and other things are unknown means you will get value of y. Okay, for the parabolic variation, this is the formula we use. And if you differentiate this with respect to x, you are going to get the slope equation and the rise equation you need to remember. And in this normal thrust and radial shear, we need to determine in this. And formula for normal thrust and radial shear, normal thrust equal to h cos theta plus v sin theta, radial shear equal to h sin theta minus v cos theta, where v is the shear force. Okay, h is the horizontal support reaction which is getting developed at supports. So one example problem, there is a 3-inch arch. It's a parabolic arch having a span of 30 meter and the central rise of 6 meter. The central rise is 6 meter. The arch carries a uniformly distributed load of intensity 30 kilonewton per meter over the left half portion. So on left half portion, that is from A to C, this arch is subjected to an UDL of 30 kilonewton per meter and a concentrated load of 60 kilonewton at 9 meter from right hand support. So from right hand support B at a distance of 9 meter, there is a 60 kilonewton force. So compute the bending moment, normal thrust and radial shear at a distance of 9 meter from left hand support. Here the left hand support is A, right hand support is B. So the question is, we need to compute the bending moment, normal thrust and the radial shear at a distance of 9 meter from left hand support. So the geometry you can write 6 meter, 30 meter, 15, 15, 60, 30. Okay, all these things with the free body diagram. HA, HB, VA, VB can write. And how to find out the support reactions and the required things, that is bending moment, normal thrust and radial shear. First, we should start with finding out the support reaction. We have the conditions of equilibrium, summation of Fy equal to 0, summation of Fx equal to 0 and summation of moment equal to 0. So summation of Fy or summation of vertical forces equal to 0, Va towards up, Vb towards up, okay, positive, minus 30 into 15, 30 throughout a span of 15 meter, 30 into 15, and then 60 kilonewton towards down. You can send it to RHS side so that it will become positive. So Va plus Vb equal to 510. So that is one equation you have. And then there is no horizontal force at all, so that are not necessary to go for using summation of Fx or summation of H equal to 0 here. And you can take a moment about any one support. So summation of MA equal to 0, it is taken here. So when it comes to moment about A, H and VA, it is passing through A so that it is 0. And then next, it is 30 kilonewton over a span of 15 meter is acting. So 30 into 15. And if you convert that into point load, it will act center. So that distance is 15 by 2. So 15 into 30 into 15 by 2. And that is trying to rotate in clockwise positive. And then 60 into distance is 30 minus 9, that is 21 meter, and trying to rotate in clockwise direction. And then VB at a distance of 30 meter, trying to rotate in anti-clockwise direction. So minus VB into 30 meter. So 30 into 15, that is positive. 60 into 21, that is positive. VB into 30, it is negative. Okay, so that is what it is written here. So that only one unknown, that is VB, will get 154.5 kilonewton. If you substitute this value in this equation, we are going to get VB value, VA value, that is 510 minus 154.5, that is will get 355.5 kilonewton. So we are done with finding out support reactions. Uh, but even another support reaction is there, that is H we need to determine. So for this, we can take a moment about C equal to 0. That is also one known thing. So this is an hinge, right? So summation of moment about C equal to 0. If you take that, any one side part you can go for taking. So one side part it is taken, right hand side portion it is taken. So H into perpendicular distance is 6, trying to rotate in clockwise positive. VB into 15, trying to rotate in anti-clockwise direction negative. And then 60 into 15 minus 9, that is 6 meter. So you can see here 60 into 6 meter, H into 6 positive, and VB into 15, VB is 154.5, trying to rotate in anti-clockwise direction minus. So that we'll get H value as 326.25. Okay, so resultant of H and VA, resultant of VB and H can be determined. So that is nothing but RA and RB. So RA will be equal to root of VA square plus H square. RB equal to root of VB square plus H square. If you do so, we are going to get the value of RA as 482.51 and RB as 360.98 kilonewton. Okay, so we are done with finding out the support reactions. And now we need to calculate the bending moment. For finding out the bending moment, we need to have the vertical ordinate height for the purpose of taking moment at any distance x. We know that a rise equation y equal to 4 times of h divided by L square into x minus L minus x. So in this, if you substitute for value of span L and rise, central rise h, so that is 6, 30 square and 30. We'll get equation y equal to simplified equation 0.8 times of x minus 0.027 x square. And if we differentiate this, we'll get dy by dx equal to 0.8 times of 8 minus 0.054 times of x, so which is nothing but tan theta. And when it comes to bending moment part, so moment at A and moment at C and D is 0. Those are all the known things. Those are all the hinged points. And we can take a moment at D. D here we are terming as like where exactly we need to find out the moment. In the question, it is mentioned that at a distance of 9 meter from left hand support. So the distance of 9 meter from left hand support means in this at a distance of 9 meter, value of V. Point D, it is taken here, it is shown also. So at this point, what is the vertical ordinate height? We can determine if we substitute the value of x. And then if we take moment at this point, we can determine the maximum moment. Maximum moment between C and B will act at D only. So that is why it is taken as MD. And 154.5 into 9. 154.5 is nothing but VB. VB into 9 is the distance from that B to D. And then minus 326.25 into YD. See, this 326.25 is nothing but H. Okay, H into YD. So that is moment value. Okay, so that moment at D will be minus 245 kilonewton meter we are going to get. So this yd, the expression for y is substituted. 0.8 times of x is substituted as 9 minus 0.027 into x square. X in place of x, 9 will be substituting 9 square. Okay, if we substitute, so we'll get the moment at D as minus 245 kilo Newton. And then between AC, the maximum bending moment may experience at midspan, due to which it is subjected to UDL force. Okay, at a distance mx means a section is taken at a distance of 7.5 meter, that is half of 15 meter. And if we take moment va into 7.5, okay, trying to rotate in clockwise positive, and then minus 30 into 7.5 into 7.5 by 2. So 30 is the intensity, and distance is 7.5, and that point load will be located at a distance of half of 7.5, and trying to rotate in anti-clockwise direction, so that is y minus, and then h into yx, and for yx at a distance of 7.5 meter, right? So at the place of x we can substitute 7.5. Okay, h value is minus 326.25 into 0.8 into 7.5 minus 0.027 into 7.5 square. If we substitute everything, we'll get the bending moment at section X is 360.5 kilonewton meter. So it is positive sign convention, so sagging bending moment, and at MD it is negative sign convention, so it is hogging bending moment. Okay, so we are done with finding out the bending moment at a distance of uh, like 7.5 meter from A, and at a distance of 9 meter from suppose B. And in question, it is asked to determine bending moment at a distance of 9 meter. Okay, so for that, we can take moment at a distance of 9 meter from left hand support. So if you do so, you will get 349 kilonewton meter, that is sagging bending moment will get. So same procedure what we followed here, but in place of 7.5 meter, we need to place 9 meter. Okay, remaining things are same. If we do so, we will get 349 kilonewton meter. Okay. And then for finding out the normal thrust and radial shear, you come for at a distance of 9 meter. The horizontal reaction it is 326.25, and shear force at a distance of 9 meter is V equal to VA towards up, that value is 355.5 minus 30 into 9. 30 is the intensity, 30 kilonewton meter per meter. So 9 meter length we are multiplying with, so that we'll get the value of shear as 85.5 kilonewton. So H value we know, V value we know. For finding out theta, we know that tan theta equal to that equation. We have differentiated the equation y, right?
Okay, we are done for the day.